Welcome to Saal 3. Our next talk is called Reverse Engineering DisplayLink Devices. It's about Linux support for USB graphic adapters, and it's going to be held by Florian Echtler. I'm very excited to hear about that, so please give a round of applause to the speaker.
Okay, yeah. Good evening, everybody. Thanks for coming to my talk. My name is Florian Echtler, and I'd like to tell you a bit about what Chris Hodges and I have done in order to be able to use DisplayLink graphics cards on Linux and other open operating systems. So at first, I'd like to introduce you to DisplayLink devices if you haven't seen them already. They're actually quite useful. They're USB graphic cards, quite cheap, around maybe 50 euros. They have DVI output or HDMI if you want. And in contrast to other USB graphic cards which you could buy earlier, they actually use compression in order to get more bandwidth out of the USB bus. And they don't offer any sort of open source drivers or Linux drivers. If you ask, of course, you get something like, yeah, we're working on it, but then you don't hear anything else. So we decided to just look how these things work and installed the Windows driver in a virtual machine on Windows XP and attached the device and listened with USB Mon on the host computer. Unfortunately, as you might see from this excerpt somewhere from the dump, it's pretty much encrypted, so this is supposed to be just a black screen. And yeah, it's safe to conclude that this is some kind of encryption. Of course, this begs the question why they do use encryption at all, but this is for a different part probably. Okay, so we were a bit surprised to see this and then thought about what to do next. So of course we cracked the device open and had a look inside and found exactly 3 chips. One really, really big ASIC, which you can probably see here if you look hard enough, which is this one, and besides just the DVI encoder and DDR RAM. So we didn't have the equipment to sniff any of the data going over the bus here, and we didn't have any tech to look inside the ASIC itself, so tough luck. We had to use some different method. Okay, so we had to try to crack the encryption in some way, and I'll try to tell you a bit about how we did this. The first idea is pretty simple. We just took the log, wrote a Python script to dump this to the device again, and we did this with the first initialization sequence, and what we got was a static Windows desktop image. So this already allowed us some conclusions. As the log worked on different devices, it looked that the encryption wasn't hardware dependent in any way. So crack one device and you've cracked all of them, which is of course a bonus. When you look at the data, which is sent to the device, then you have some small blocks around maybe at most 4 kilobytes, and we have 2 very big blocks. And these blocks have to be sent in the correct sequence, otherwise the device starts flashing wildly and crashes. And this, again, allows the conclusion that maybe a stream cipher is used here. So we just have a key which has a certain length, and data is always XORed with that key. And if you reach the end of it, then you just take the length modulus, the length of the key, and start again. We inserted some delays between the blocks, and therefore we saw that the first one of the 2 big blocks just clears the frame buffer, and the second block transfers the desktop contents. So this was pretty much where we were at that point. One interesting part was that all of this were in fact, USB bulk transfers. So everything the device does is bulk transfer, with one small exception, which is at the very start. When you initialize the device, then some control transfers happen which are not encrypted. So for example, what you get here is the readout of the monitor description. Here, 64 bytes are read twice and 3 bytes additionally, so you get a total of 131 bytes. This is the EDID block plus 3 length bytes, and this is exactly the EDID data of the attached monitor. So at this point, encryption doesn't yet happen. And there's one interesting control transfer in this entire initialization sequence, which is just 16 bytes of seemingly garbage. What's most interesting is these repeat after each device initialization, but sometimes after you restart the virtual machine, the same bytes occur again. So again, we started thinking that this might be a crypto key, and so here were some sample sequences which look pretty random. Now Chris had a really good idea, and we just entered those into Google. Why not? And And as you might already think, we actually got hits. And this was quite surprising at first, but after some reading, we found out that this is simply standard output from the standard Microsoft random number generator. So, of course, this also explains why you sometimes see it again after you restart the VM, because the system is exactly in the same state as during the last boot. For some additional information on this, you can read the link afterwards. But okay, so we were pretty certain at that point that this data is actually the crypto key. But of course, this didn't help very much at that point, because we still didn't know what the algorithm used for the encryption actually was. So we tried some very basic crypt analysis, which is just to compare the crypto text with itself, shifted by a certain length. So you take some buffer of crypto data, and for half of the length of this buffer, you just compare byte in location 1 to byte in location 1 plus some certain offset. And if these bytes are equal, then you increase a counter. And the results were quite convincing. So you can see them here. So these are actually sorted by count. So it's pretty certain to say that the key length is 4095, because this is the maximum and all of the multiples of this. And this is, of course, 2 to the 12th power minus 1, as most of you might already have seen. And this points again to a specific kind of pseudo-random number generator, which is called linear feedback shift register. And this is also interesting because these registers are often used in FPGA and ASIC programming, because they are very fast, and so this might have been a convenient choice for the developers of this device. Of course, this doesn't help too much if you know the key length. Now, what you need in the end is the key stream generator. So our two assumptions were that we have a stream cipher, we have LFSR, random number generator, a maximal LFSR, which means that it actually uses the maximum possible period, so which is 4095 bytes. Okay, so now we had to try and find the keystream generator in some way, and we started with IDA Pro freeware to just disassemble the driver module. And we quickly found that it uses libUSB internally, which was statically linked into the driver, which might raise some interesting licensing questions. And yeah, the data was just submitted through one of the libUSB calls, and what we tried at first was to work backwards from there, look at the call graph, and look where the data actually comes from. Unfortunately, the driver was written in C++, and it's not that funny to try to disassemble virtual functions. in the end, we settled on a much simpler approach here, and we just looked for, in the assembler code, for an immediate value of 4095, because at some point the routine has to generate that much data. And we quickly found such a subroutine which consisted of 3 nested loops, and which actually does contain, does generate 4095 bytes of data. And most interestingly, it contains a test against this value. And when you check, for example, Wikipedia on LFSRs, you always need a generator polynomial, and only certain ones of these generator polynomials are actually generating a maximal LFSR. Well, and this one is one of them, so we were pretty certain at that point that we had found the key stream generator. Sorry. Okay, so one other interesting question is where the 16-byte key, which we found pretty much in the beginning, fits in, because the key stream generated by this LFSR is actually always the same. It just starts with some initial value, which is hard-coded in the data, and generates 4095 bytes of data. Actually, it generates 11 times this amount in order to be able to use the buffer more efficiently, so you don't always have to wrap around. But in any case, the random number hasn't been used up to this point. So what we at first were a bit surprised is that the LFSR data also generates a reverse mapping table, which gives you the offset for each value, for each random number, basically. And so the starting offset at which the encryption begins is taken from this reverse mapping table. And the index for this table, again, is generated from the key. So the key simply tells you where to start in the actual key stream. And this is also obviously how the device itself works then. The CRC of this key is just fed into the LFSR on the device, which then starts generating the same key stream as in the driver. So this is in fact a standard CRC12, and it looks like the device doesn't even generate the data, doesn't even generate the entire key in memory, but just always pulls a single value from the shift register and then advances it by 1. Okay, so one interesting piece is, of course, that LFSRs which are loaded with 0 will always output 0. So if you have a CRC12 of 0, this should just disable the encryption entirely. For some reason which we haven't been able to figure out yet, it doesn't work with every key, but there are some keys which do have a CRC12 of 0 and which do disable the encryption, and we found these in the driver, basically. Most importantly, they are in the driver because the driver has a debug flag which just turns off the entire encryption if you set it to 1. So in fact, we might have found this earlier, but it's still funny to know, to be able to decrypt the earlier captured data. So, okay, so at this point, we were now able to capture unencrypted communication between the device and the Windows driver. And so we were now able to start having a look at the graphics protocol. The protocol itself is in fact quite simple. I won't go into much detail here. So the most important command is just this graphics command. This is more or less the base value. And you have 2 flags which can be added, and you have 3 subcommands. Most important are these 2, basically. The device internally is organized in 2 separate frame buffers. So you have a 16-bit frame buffer, which is used in 16-bit color depth and in 24-bit color depth. And when you use 24-bit color depth, you get a secondary 8-bit frame buffer, which delivers the missing 8 bits of color data. Yeah, and you can, you have basically just linear memory in the device, 16 megabytes. You can do copy on device. You can write data in a certain RLE, run length encoded well, not too efficient encoding, but this is, for example, used by the driver to clear the frame buffer. So for big runs of similar colors, this is quite efficient, in fact. And you can, of course, just write raw data to the device. And every one of these commands is followed by a 3-byte address and 1-byte pixel count. This is, in fact, quite important. This is not the count of bytes which follow, but it's the count of pixels which are in the end written to the frame buffer. So, for example, for the run length encoding, you get a much higher pixel count than what's actually following in terms of data. Okay, there are also some auxiliary commands. You have a number of registers which, for example, to determine where the frame buffer starts, so you can do vertical scrolling by just setting a frame buffer offset. Most of these values we have just taken from what the Windows driver sends to enable standard video modes. So these are the blanking, offset, and so on values. There's a flush buffer command, which causes probably all queued commands to be executed. And there's one very important command which sets the Huffman encryption table. Yeah, as I said, if you're interested in more details, please see the references. Otherwise, I think it would be pretty boring. Now I'll come to a small intermission, which is how DisplayLink, the corporation who manufactures these things, reacted to the entire stuff. So this was pretty. This first reverse engineering steps happened about almost exactly a year ago, in fact. And for half a year after that, nobody pretty much looked at this stuff until somebody else, Roberto de Ioris, started writing an XORG driver. And suddenly DisplayLink started, we're going to release our great open source library, which is called libdlo, and which is open source but has two big shortcomings. The init sequences were in fact still encrypted, so there were still just big binary blobs which were dumped to the device. And the compression, especially the Huffman-based compression, which is the defining feature more or less of these things, was still missing. So at this point we decided that we would have to figure out the Huffman compression by itself, or by ourselves, and started to have a look at this. I already mentioned the run length compression. The Huffman compression, with something like gzip uses, is of course much more efficient for picture data. Instead of the run length compression might actually work quite well for things like desktop images or just user interfaces. But as soon as you get pictures or video, the Huffman compression, of course, is much more efficient. One thing which I also already mentioned earlier is that there is a 4.5 kilobyte binary blob which is sent with this command, and this command occurs nowhere else, just in the initialization with this blob. And if you leave this command out, the device still works as it does otherwise, just compressed data doesn't work anymore. So this is pretty certainly the Huffman table. And okay, so looking at this table didn't really yield much results, so we started again by just analyzing data which we sent from the Windows driver. So the two most basic results were that the pixel values aren't encoded themselves, but the difference to the previous pixel. And when you start a new command, the previous pixel is set to black, so to 0. And the second finding was that bit sequence of 0 bits encodes a difference of null. So this is also in Huffman compression, shortest sequences correspond to the most frequent numbers. And of course, in images, as you have pretty much often, you have runs of similar color still. 0 is the most common difference value. Now, the next step was to just treat this as another crypto problem and find the table again, which gives you the Huffman sequence for a certain pixel value, or rather difference value. And so we just tried basically a chosen plaintext attack, which means we just send a suitable color pattern through the driver, through the Windows driver, for every difference value which might occur in the data. As the device separates into 16 and 8-bit commands, and those are treated completely separately, the main problem is just to find these 2 to the power of 16 difference values. And this isn't that much, in fact, so we just tried a brute force approach here. And now here's the pattern which we used for finding the data. In fact, in real, it was a bit more complex, but this serves to illustrate how it actually works. So the background here is black, and this pattern has the color for which we want to find the difference value. And so if you go from left to right through this row, you get the differences of plus n from black to the color, minus n from the color to black, and the same again twice. And below here, you get again a difference value of n. Then we get a difference value of 0 because the color stays the same. And at the end, we get a step back of minus n to the color black. And so this is, in fact, pretty easy to find these sequences in the compressed data stream. And okay, yeah. So we try, the approach is basically to generate this pattern for every color n in 16-bit on a black background, and you get 2 different bit sequences, as I mentioned. The one starts with 0, 0. Of course, all of them start with 0, 0 as the first pixel of every row is black, and the starting value is also 0. So we get the sequence for a difference of 0, then we get 2 pairs of plus and minus n, and the rest is zeros, and we get plus n to zeros minus n. And when we now strip the leading 2 zeros and try to find the longest repeating substring here, then we end up with the sequence for just plus n minus n. And this now we can compare with this sequence and find the longest common prefix. And when we also have found this, then we get the 2 separate sequences, plus n and minus n. One sort of sanity check which can be done here is that the 2 sequences should always be of the same length, because the difference is equally likely to occur in positive direction as well in negative direction. We assume that the company actually analyzed images and tried to find a universally suitable Huffman code which covers a wide range of different images, like, for example, video images, desktop backgrounds, window decorations, and so on. And in such a wide sample of images, you should always have the same sequence of the same probability for each of those sequences. Okay, so in fact this turned out to be easier than we thought. We automated this with a bit of shell scripting. So we had a script running in the virtual machine, which simply set a new desktop background after some seconds. This would generate data sent by the driver to the device and captured by USB-Mon. And that in order for this to be a bit faster, we just put 32 different color values in every one of those images, so 32 patterns of the sort which you saw earlier. And the total running time was about 4 hours. This yielded most of the patterns, though not all of them, because the method doesn't work when the pattern itself is split at the boundary between 2 commands. If you remember, every command can only generate up to 256 pixels, and depending on where the command boundary is, it might just split the pattern apart, and then of course the string analysis doesn't work. So what we did for these values, which we couldn't capture, we just shifted the pattern by some pixels and repeated the process. And by doing this, we also got the rest of the missing patterns. So it looks like some weeks ago somebody found erroneous sequence, so it may be that there are still some sequences which escaped our attempts. Okay, now I'm almost at the end already, and but I come to one interesting piece before I finish. So we have still two things which are unsolved and which I would like to invite you to also maybe give a look if you want to. So the first one is pretty trivial. This is that we don't have the Huffman sequences for the 8-bit mode yet. So this should be rather trivial because you just have to repeat the process with 8-bit with colors which differ in the last 8 bits. The important part, however, is the compressed Huffman table. So we have the Huffman table is a binary tree which has up to 30 levels. So the longest bit sequences are 30 bits. And there are 2 to the power of 16 leaf values, all of the difference values. And this entire tree is obviously somehow represented in the 4.5 kilobyte table which is sent to the device. And so the tree doesn't seem to have any obvious structure, but somehow it's still represented in there. So yeah, here we have some sample entries. The structure seems to look like we have 512 records, each of which has 9 bytes. This is particularly evident in the last maybe 135 or so entries, which look like they are empty, and they all have this structure. And here's also some sample entries which look like they correspond to these 2 leaf node values. So they have, both of them have a bit depth or a bit length for the code of 6 bits. So these are pretty often occurring differences. And you can see, for example, this is 2113, this is 2081. And it looks like this record somehow contains pointers to the leaf values, and these maybe contain the bit depth. But exactly how these are interrelated, we haven't yet figured out. So this is, of course, not strictly necessary to operate the device because we do know the Huffman table. We can keep it in memory. It's just around 320 kilobytes. However, for a driver, for example, for a kernel driver, it would still be nice to have the compressed version, which is uncompressed on the fly. Okay. Oh, no. So yeah, I'm already at the end of my talk, a bit faster than expected. So I'd like to thank some people, first of all, Roberto Di Ioris, Markus Glocker, Sven Killig, and other people who were actually brave enough to use this stuff on their DisplayLink devices and write kernel drivers, for example, for a FreeBSD, for Xorg, or a terminal emulator. DisplayLink, in fact, at some point started donating devices to us, so they also deserve a thank you. Their acceptance of the open source stuff is still somewhat grudging, but I think they have realized that it's here to stay. Also, many thanks to my co-author, Chris Hodges, and yeah, to you for your attention. Thanks. As we still have quite a lot of time, are there any questions?
Right. I would ask anyone who has a question to line up on that microphone back there, please.
Yeah.
Hi there. Being slightly dumb, I didn't get the idea of the Huffman table. You said there's 4.5K, and this gets sent by the driver to the device.
Exactly. So this is 4.5K, and it somehow so this Huffman table can be obviously sent dynamically by the driver. It's always the same, but they have the option to set a dynamic one, and it somehow contains the instructions for the device on how to decode the Huffman values again into raw binary data. And yeah.
So, first thing, illegally, you could probably nick this binary blob and send it, purely for testing purposes, send the one you'd nicked from the Windows driver and send that down there. But obviously, I guess to encode the data, you need to know how to use the table, be it your uncompressed one or their 4.5K one.
Well, yes and no. So we actually do send this table, so it's actually just as a binary blob included in the driver, but we still do need to know the 320K plane mapping from differences to values, because the table, at this moment, this small table can just be interpreted by the device and by nothing else. And the big table just is a big binary blob coming along with the driver at the moment, which is used in the software to compress data. And the small table is used just on the device to decompress again. But of course, there's a connection between these two.
Right, yeah, thanks. That's cleared it up a little bit for me.
Okay,
Thank you.
You're welcome.
A question regarding the tables. Because maybe you can take the difference. So maybe you have a Windows driver, you make a blue picture, and then you take the original table, and then you try with a table you make up and see, no, it's not blue, and then you try as long as you get a blue picture.
But the Windows driver doesn't change the table, unfortunately. It always uses the same one. So
Okay, so the Windows driver uses the compressed table and knows how to use it. And so you need a table where you know how to use the compressed table. And you do not know how to get the original table from the compressed table. So
Exactly.
try every table that are possible and compare them with the compressed table.
Well,
So you make a table and you put a picture that should be blue and that is not blue. So you say it's the wrong table. Take the next one. And then you try, and then you maybe get the right table.
that would work, but you would have to try every binary tree which has a depth of at least 30. So these are very, very many trees.
Have you calculated the efforts? What is the effort, the cost of the algorithm? Have you calculated it?
No, not yet. Well, it might be doable. I just thought that this is unfeasible for brute force, but maybe you're right. Well,
Take a logic analyzer and detect the DVI signal and see, okay, it's a blue.
Okay.
It's a green, it's a red, and then you try, and then it triggers on red and says, book, that's red.
Okay, yeah, that might be an idea, in fact. Thanks.
I was wondering, DisplayLink started on their own open source driver. You were already working on that.
Yes.
Right now you're trying to crack the last bits. It seems like DisplayLink isn't against having an open source driver, and it seems that you are willing to write it for them. Did you try to contact the developers and, for example, ask them about the compressed Huffman table and the...
Well, yes, I did, but there wasn't any real reaction. So it looks like they are considering the compression, or maybe even the compression of the table itself, their main achievement, and so they're still very quiet on this. And they're also not, it doesn't look like they would like to integrate this into their own driver. So, yeah, they're somewhere between helpful and very quiet. They're not really obstructing anything, but they're not quite convinced, obviously.
One question about the binary drivers that you, the binary tables that you have to send over to get it to work. Assuming you are able to write a driver that really does the compression on the computer side, but you don't know how the small table does the decompression on the device.
Exactly.
Would you even be able to include this into any kernel that has a strict philosophy about having non-free binary blobs of firmware?
I think that's not a question for me to answer because I'm definitely not an expert in that direction. I suppose that it's not really a firmware. So, yeah, I don't know.
Okay, but maybe I should rephrase it and ask, was that a motivation for you to try and understand how you can fit the complete Huffman table into only 4 kilobyte?
Well, yes, definitely, because then you would also be able to actually generate a new table. For example, if you know that you are going to play a certain kind of video, then you might actually generate an optimized table for this video. So maybe you could even extract it somehow from MPEG data or something like this. So this would definitely still be interesting. And it would, of course, clear up the licensing issue because then everything would be free in this driver.
Right, I see there are no more questions. There's another one, would you please? Oh, I'll get it for you. We'll make an exception.
So you mentioned that the Windows driver has this libUSB static link to their obviously unsourced driver.
Yes.
Have you considered contacting the Software Freedom Law Center that they might push them using this information into an agreement that they would release this Huffman table thingy and they wouldn't be sued for that little libUSB incident?
Well, no, we didn't do this. I thought about it briefly, but I think, yeah, it's, well, I spoken bluntly, I didn't want to piss them off because they were rather a little bit more on the helpful side of things, so I thought it would be nasty to try and pull out the lawyers. And I'm not quite sure if it's actually a violation of the license if they do this. So if you know anything more specific about this, I'd curious to hear about this. But yeah, so far I didn't consider it necessary, basically.
Right, we're at the end then. Thanks again to the speaker.